Thank you very much for the introduction. So, actually, this is my first on-site international conference these 3 years, and first time go out of Japan these 3 years. I'm very happy to hear, to be here. So, thank you very much for organizers to inviting me. So, yes, on the lunchtime, I was asked by several people that why did you add 2 exclamation marks here? I will explain it later, but it's a kind of uniqueness condition as usual, and I call it usually WKL W1, but you can call it as you like. It's a topic of reverse mathematics, constructive reverse mathematics. In earlier talks, there are some keywords from reverse mathematics this time. I didn't expect it, so I prepared several slides about reverse mathematics here, and especially for constructive one, something about constructive one. And the important topic, important theorem or lemma is weak-Kenish lemma today, with some uniqueness condition. And WKL W1 is a kind of weak-Kenish lemma with a kind certain condition for uniqueness. So the idea of so what I'm doing, by the way, this is a joint work with Makoto Fujiwara. What we've done is decomposing this WKL W1 into some kind of choice action and logical principles. So, by the way, I changed my title slightly not on the decomposition, but I just changed on somebody can propose better decomposition of WKL W1. So just free to do it, and just feel free to do it, but it's a kind of suggestion. So what is reverse mathematics? I think you already know about. So usual mathematics is to prove some theorems from actions, but usually, like Occam's razor, we prefer less and less assumptions, and sometimes the conclusion, so let's call assumption A and the conclusion B. Sometimes when we sharpen the proof, then sometimes the conclusion B is also derivable assumption. Conclusion B also derive the assumption A. That is the reverse direction. So that means A and B are equivalent. So so this is the idea of reverse mathematics. And in reverse mathematics classical setting, we take some kind of set comprehension A, and then we can classify mathematical theorems with set comprehension action. And Friedman and Simpson's famous reverse math is reverse mathematics is classical logic, and they use set comprehension action as a kind of measure, and so big 5 systems are very famous, and some people may think this is the reverse mathematics. And this is the language of classical reverse mathematics, usually called L2. It contains basic arithmetic, basic first-order arithmetic, and it contains set variables for sets of natural numbers, and they have binary relations for membership. The base system, usual base system. So over this system, we can prove the equivalence between set comprehension action and mathematical theorems. The base base system is called usually RCA node that contains basic arithmetic and sigma 01 induction and delta 01 comprehension, which means recursive comprehension. So the minimum model of RCA node is a minimum omega model. That means first order part is standard omega, is the set of all recursive sets. And one of weakest but most important system of reverse mathematics is called WKL, which consists of weak k-niche lemma and this RCA node. So let's recall some terminology for binary trees. Binary tree is a subset of finite binary sequence, so finite 0-1 sequence closed on the initial segment. And if we call T is infinite, if for any n there is a branch in T which is length n. By the way, this symbol just denotes the length of this finite sequence. And the path of a binary tree T is a function such that all initial segment of it is in the tree T. So I use this symbol overlying alpha n to indicate the nth initial segment of alpha. So now we are ready to define weak k-niche lemma. Every infinite binary tree has a path like this. Very simple. And this is, I just checked Simpson's book, which are equivalent to weak k-niche lemma. It varies over RCA node. It varies some important theorems of basic analysis and Gödel's incompleteness theorem and some property from algebra and ordinary differential equation, etc. And the kind of weakest axiom of choice. So it's very important axiom in classical reverse mathematics. And we can, of course, we consider a constructive version of it. And usual mathematics based on classical logic, but constructive mathematics we based on intuitionistic logic. It's the good thing doing reverse mathematics on constructive setting is we can analyze mathematical theorems more detail. So we can characterize mathematical theorems with choice principle, which asserts existence of a function. It can be regarded as a characteristic function of a set sometimes. And we can also extract which logical principles, which fragment of law of excluded middle or which fragment of the Morgan's law are necessary and sufficient to prove the theorems. That is our idea. And this is a system for constructive reverse mathematics. Instead of set-based system, we usually use systems with first-order arithmetic and function variables and some property for functions. We have a lambda operator, and we have a recursor which allows primitive recursion. And the system consists, and we also add all function symbols for primitive recursive function, but this is not essential. The axiom of EL0, what we use as a base theory today, is it consists of basic rule of basic arithmetics and very basic pi-0-0 induction and lambda conversion and primitive recursion and quantifier-free axiom of choice. So for all x, there exists y with some condition, then we can take this y as a function, as a strings function for any quantifier-free formula. But here I use pi-0. It's same. For it's same. We can allow it pi-0 formulas. By the way, pi-0 formula means just arithmetical, just formulas without any quantifiers for function variables, any unbounded number variables. Just it has bounded number quantifiers. Okay, let's compare classical system and our system. Of course, RCA not use classical logic, and they use set-based language and allowing primitive recursion. For EL0, intuitionistic logic and function-based language. Why we use this system? It's for me, at least for me, I have a clear reason to use it. Using function-based system, we have a decidability for all atomic formulas, lobe excluded middle for all atomic formulas. Then we can prove by induction on the construction of formula, then we have lobe excluded middle for whole pi-0-0 formulas. And maybe you remember that EL0 has only pi-0-0 induction, but actually it has a recursal, so it allows whole primitive recursion and also sigma 01 induction. And we can interpret this set-based language and function-based language. And I'm not sure this is the right citation, right reference for this topic, but I think many people already know it. But this system has a kind of conservativity for pi-0-2 sentence. So in particular, what we can prove in RCA not classical system. Yeah?
Maybe when you finish, can you go back to the previous slide of the specification?
Yeah.
Yeah, it's a good time. I just wanted to make sure I was understanding things. So, okay, so you've got it's finitely simply typed, right? So you and all terms are presumably typed. So the lambda operation.
Okay, so.
So application is like is compatible typing.
Yes, actually we have so we don't use this is used like this. We put here just a number variables, and we have here just number term.
Also, you only abstract over
yeah.
over that
yes.
type.
Yes.
Okay, so everything's just everything's either a function or natural numbers.
Yes.
Okay.
Yes.
And you only have first order quality. So
yes.
The formula class like pi-0, 0, the only equations are at type 0.
Yes. Yes. So yes, that's a good point. We don't have any equality for functions. So yes, that make system easier. All atomic formula has a decidability property. It's easy.
And so and quantifier-free axiom for 0, 0. This just is specifying that the x and y are of type 0.
Yeah. I'm sorry for that. Yes. Here I number variables are here. Yes. Yeah.
And then just on the slide about the conservativity.
Yes. This one.
You have to just to check. This is like you have to do like a witnessing argument here, right? Because you don't have sigma 1 induction.
Yeah.
You have to witness the existential by a primitive recursion.
Yes. Yes.
Okay.
Yes. Yes, so actually this system essentially has a sigma 1 induction, and we can interpret one to the other, and yeah, we can easily prove what we proved in intuitionist system, in classical system, but we have further to conservativity from classical system into EL0 intuitionist system. So we can so first order part we have some common part of language, and what we could prove in RCA node in for Python 2 sentence, we can also prove in EL0. So in particular, we have these systems have the same consistency strengths. And okay, let's consider about weak K-niche lemma in intuitionist system. This is proved essentially by Joseph Berger and Professor Ishihara and Professor Schuster some time ago. And weak K-niche lemma are characterized with pi01 AC disjunction and sigma 01 de Morgan's law. Here I described the condition, what it means. So for all x, ax or bx holds, and a and b both are in pi01 formula, then we have a function which tells which are right for each x. This is a pi01 axiom, pi01 AC disjunction. And sigma 01 de Morgan's law is as usual. And if we have not A and B, then we have not A or not B for any pair of sigma 01 formulas. So this is a non-trivial direction of de Morgan's law in intuitionist logic. Then, this is the topic of today. So, weak K-niche lemma and uniqueness conditions. So, first uniqueness condition is a binary tree does not have two passes. That is, for any two strings which are distinct at some point, then it goes outside of T like this. And in classical, in intuitionistic setting, we can consider another version. It's a contraposition. A binary tree has at most one path if for any alpha and beta. If both are paths of T, then they are identical. So, of course, in intuitionistic setting, they are not equivalent. Bar notation. This is the initial fragment of the string infinite sequence. So I go back here. This one. Alpha over n is this one. Alpha 0, the string first n strings. Okay, then we can define WKL with uniqueness condition. So WKL bound asserts that every infinite binary sequence which does not have two passes has a path. So and another one is WKL double bound. Every infinite binary tree which has at most one path has a path. So the easy observation is, so the first uniqueness condition is stronger than the second one. That means WKL bound has a strong assumption. So WKL bound is weaker than WKL double bound. So it's easier direction. And this is easy, but but these implications are not reversible. So first, let me talk about the history of these actions. WKL ban is first introduced Berger and Professor Ishihara, and Joan Moskvakis introduced WKL double ban, and in her paper, it was, I think, 2012, she gave a model of, she gave a detailed investigation of WKL double ban and this WKL ban. First, she used modified realizability to give a model for this WKL ban, but not WKL double ban. So in the next slide, I will show that WKL double ban introduced a fragment of De Morgan's law which are not modified realizable. But this WKL ban, it shows that it is equivalent to a Fan theorem for decidable Fan, which is modified realizable. That means we have a model for WKL ban, but not WKL double ban. So this part, this arrow, is not reversible. And another separation problem is here. Cleanness function realizability. It gives, so using cleanness function realizability for EL plus Markov's principle or with some classical logic, then we can construct a model of WKL double ban. In the later slide, we will see that this WKL double ban is decomposed as with some fragment of another fragment of De Morgan's law, which are cleanly realizable, and this is decomposed also in with a fragment of choice action which are cleanly realizable. But this model is it is not a model for WKL, because the model for WKL double ban could be constructed with the universe of whole total recursive functions. In that setting, we have a recursive binary tree without any recursive path. So even with the classical logic, we cannot prove there's a path of WKL. There is a path of the tree. So we have a model of this WKL double ban and not WKL. So this is a separation. And what is proved by Joan is not only that one. She gave first characterization of WKL double ban. She proves that WKL double ban is equivalent with double negation, a kind of double negation of WKL plus Pi0 and Morgan's law. So what is this dn WKL? That is, we add double negation in the conclusion of usual WKL here. So if T is an infinite binary tree, then it's difficult to pronounce. Not T has a path. And Pi0 and Morgan's law is as you expected. If we have A and not A and B, then not A or not B for any Pi0 formulas. Then, what is this system M? It's her original formalization is slightly different, but we can regard it as a EL0 plus full induction scheme and axiom of unique choice for all x exist y such that ax y. Then we can take the series, we can take an infinite sequence alpha such that for all x, ax, alpha x. Not only for quantifier free formula, but for any formula A. So this is a kind of, how to say, this is a kind of very Bishop style setting. It has full induction, it has full unique choice. Of course, it's a bit stronger than our EL0. So, and what we can observe here is this M, what we have to note here is this M does not prove DN-WKL because, as I told before, there is a recursive binary tree with no recursive path. So this and this and the universe, so we can construct the model of M with the whole total recursive functions. That means we can construct a recursive tree without any path here. So this M does not prove the DN-WKL. And yes, so John characterized this WKL double band as follows, but our question is, the system M is slightly stronger than EL0. It has full induction and actually some strong induction scheme is used in her proof, and stronger unique choice is used also. Okay, can we modify this proof in our setting? So can we characterize this WKL double band over weaker setting? That is our question. By the way, why I prefer this system is just what I like to compare classical setting and intuitionist setting. So EL0 is a kind of we have a interpretation, and it makes easier to compare classical result and intuitionistic result. Okay, let's do it. So this is what we done first. WKL double band is characterized. This is equivalent with these two sets of actions. First one is Python AC disjunction with band, and the Python mode control and DN-WKL. So this part is given by Moskvakis' original characterization. So what we did is just extract what kind of fragment of choice is needed. And also we showed that a stronger induction scheme used in her proof is not essential. Here, Python AC disjunction band is like this. So here again we have a band which indicates uniqueness, that for all Ax and B, for all X, if we have Ax or Bx and we don't have both of them at the same time, then we have a function such that which tells this A holds or B holds for all X. So if A and B are quantifier-free formula, then or pi00 formula we have already have in EL0, but here it's a pi01 formula, so it's not automatically we have in the system. And actually we don't have it. And another characterization is a slightly generalized version. Python bound BAC, that is, so what is generalized is here. So this AX hold or BX hold, one of two, just one of two hold is not essential. So for all x, there exists unique y less than g of x, such that AXY holds. So then we have a sequence alpha, which tells for all x which one is the right one we wanted.
All G?
Hmm?
All G?
Yes, we have a universal quantifier outside here. So yes, so the essential part is we have unique one within certain bounded area. Then we can choose the string. That is the idea. And the next part is what's this Dn WKL? What we did is, yes, it is also decomposed as follows. Dn WKL is equivalent to a kind of double negation shift and a kind of double negation of action of choice for disjunctive formula. So the first double negation shift is as follows. If we have for all x, not AX or BX, then we can shift this double negation in the front. And this part, Dn pi 01 AC disjunction is just add double negation in the conclusion of Dn pi 01 AC. Yes, here. Yes. So if we omit this double negation, then that is exactly the same what we saw before. But so this Dn usually means insert double negation in the conclusion. Okay, some observation. Before some observation, we have such whole picture. So this is what is proved by Berger, Ishihara, and Schuster. And we have something similar decomposition for WKL double band. And so this part is Dn WKL, and this part, and this part is what we found. And these two kinds of a kind of choice is derived by the one AC disjunction, and these two logical principles are derived from this sigma 01 DML. So we liked this decomposition. And some observation about this pi 01 AC disjunction band. Actually, this is I'm sometimes hesitate. I call it choice because it is provable in EL0 plus sigma 01 double negation elimination. That is not A implies A for sigma 01 formula, because if we have for all x, for all y AXY, for all y BXY, where A and B are pi 01 formula this time, and exactly one of them holds, then by sigma 01 DNE yields here, from here, we have for all x, we have there is y such that not A or AXY or not BXY. Just so this part is just a negation of sigma 01 formula, so just move it. Then, so that means we have for all x, we have a witness for not a, x, y, not a or not b here, then just correct it. Then, so this is a kind of counter witness for a and b, so just correct it. Then we can construct a string what we wanted. So this looks like choice, and actually choose something, but here we know that it's rather weak choice action. And another observation is so you see this is a logical part, this is a logical part, and this can be proved EL0 plus sigma 01 double negation elimination. And what is left is here. What is left is here. But so what we know is even with classical logic, this dn pi 01 AC disjunction is not provable because WKL double bound is WKL bound, which is equivalent to Fan theorem for decidable funds. Then, if EL0 plus classical logic proves this dn WKL, then it proved Fan theorem for decidable fund. And with classical logic, it's equivalent to WKL. But we already know that this does not prove WKL. So actually, this part, dn pi 01 AC disjunction does not assert the strict existence of functions. Looks very weak, but it's something hard to prove in this setting, even with classical logic. So this is, in a sense, most non-trivial part. Sometimes I like this. Why I emphasize this part is just what I like here. And okay, I have some time. Just I give some sketch of proof. First part, WKL double bound implies De Morgan's fragment of Python fragment of De Morgan's law and dn WKL. This is just formalization of the original proof, and it's very tricky or easy but tricky. So first, WKL double bound proves dn WKL. Assume that T is an infinite binary tree without any infinite path. Then, of course, because T has no infinite path, T has at most one path. So using WKL double bound, it has an infinite path. That is a contradiction. So assuming T has no infinite path, it's incorrect. We can add another negation here. We have not T has an infinite path. It's very easy, but I like this tricky proof. And another part, WKL double bound implies Python De Morgan's law. Okay, let's assume assumption for all x ax and for all x bx. That is not the case. By the way, here a and b are pi 00 formula. Then we can construct a simple tree that it's a string of zero. String just consists of 0. That is, or for all I less than the length of I, AI implies BI. And another one is sequence consists of just one, and BI implies AI. So if I draw a tree, then it's just like this. So, like this. But because T is an infinite binary tree with at most one path. So infiniteness is guaranteed that yes, we have that we don't have for all yes, we don't have for x ax and for x bx at the same time, and at most one path is, so that guarantees T is infinite and has an at most one path. Then
definition of T is the middle and not or. The definition of T.
Yes. Sorry, here it's yes. You're right. Yeah. Then WKL double bound gives the infinite path, and let's check the first digit. Then it's all. Then that's all. So if the first digit is 0, then from this condition, if for all x x holds, then for all x bx also holds. That contradiction that gives a contradiction from the assumption, and same as for 1. Okay. So some of you may notice that this is almost same when we prove WK from WK to sigma 0 and Morgan's law. It's almost same. And remaining proof, what is not given by Joan, that is WKL double bound implies Python AC disjunction bound. Okay, let's assume we have this one or this one for all x, but exactly 1. Then, as usual, we construct a tree like this. U is a finite sequence, and for each I, Ui implies 0. Ui is equal to 0 implies for all y less than the length of y, aiy hold. And if ui is equal to 1, the other hold. So because we have for all x this one or this one. So for each, so this tree should be an infinite binary tree. We need to prove infiniteness of tree. We need induction, but it's enough if we have pi0 induction. And because of the uniqueness, we don't. The tree has at most one path. Then, okay, then just take a path, infinite path of this tree by WKL double one. Then it is a function what we wanted for this pi01 AC disjunction bound. Yes, that's it for one direction. The other direction. It's a bit complicated. We have to construct a path for given infinite binary tree with at most one path. Then, actually, this is kind of modification of pi01 AC disjunction. Here I forget to do this. and sigma 0 and Morgan's law implies WKL. So assume T is infinite binary tree with at most one path and define formula dmn like this. Exists U of length m binary sequence and concatenation of U and B is in T. So that means you have a successor with m length in T. Then, for each U, we don't have U0 have or n successor for all n, or U1 have or n successor for it. Because if both the case, then we can define a kind of subtree of T like this, and here is the part we need dnWKL. dnWKL yields both of the subtree has an infinite, not both of the subtree has an infinite path. T0. Oh, yes, sorry. Yes. Then, yes, you're right. And then it's a contradiction that T has at most one path. Okay, then we have one of the conjunction is a case because of Python and Morgan's law. Okay, then using using Python AC disjunction, we can construct a path of this 3T, because one of the disjunction of this case, it's enough to use Python AC disjunction bound. And yes, if you know the proof of sigma 0 and Morgan's law and Python AC disjunction gives WKL, then it's just a kind of weakening of the proof, weakening or strengthening, I don't know, but it's very similar to the original proof, but with uniqueness condition, we can modify it like this. Okay, and of course we can decompose this dnWKL part, but it's just a kind of, how to say, modification of the original proof. WKL implies Python AC disjunction, and this is a bit interesting part. dnWKL implies Python and Python DNS. This is constructing tree, like, so assuming for y xy, for all y bxy, for all x, not this part, then we can construct for each 3t, for each x, we can construct a 3t, and like this. If U0 is U0 is equal to 0, so this Tx consists of the sequence, all 0 sequence or all 1 sequence, and if the first digit is equal to 0, then AXI holds, and if the first digit is equal to 1, then BXI holds for all I. Then, so we have countably many trees, but we can compound them into one tree, like this. It is so just using coding of finite sequences, we can, like weaving, we can compound the tree. Then, using this dnWKL, we have not exists the path of it, which gives not for all x, y, xy, and for all x, b, xy. So compounding countably many tree into one tree is an essential part, and that's what I like. And this part is almost same as before. You proving it's just modification of Python HC disjunction and sigma zero and Morgan's law into WKL can be, modified. And maybe it's almost the time to stop. Okay, if you have a question, just.
You have 10 minutes if you want.
Oh, really? I think I have.
It started from 5. Yeah, from 5 past 6.
Okay, it's okay. Yeah, it's yeah. If you want, please ask me about this proof in the question time, and I will stop here. And what we had is like this picture, and yeah, it's quite looks like complicated, but quite interesting. And yes, if you are interested in, just ask me, and let's do it together. That's all what I wanted to talk. Thank you very much.